So in our last video, we asked the question of how do we describe the state of a subsystem of a quantum system when that quantum system is in an entangled state? And we said that there's no way that we can write down a state of just this subsystem in the conventional way that we write down states, so that that state would describe all of the properties of the subsystem in the context of the larger system. And so in this video, I will tell you the proper way that we need to do that. And that involves the idea of ensembles of quantum states. And so let me start with the definition of an ensemble. And so an ensemble is simply a collection of states, so psi I, and along with each state we have a probability. So pi would be a probability, and we require that the sum of these p's is equal to 1. And so the idea is that given an ensemble, we can talk about expectation values of observables in that ensemble, just like we would talk about expectation values in specific states. So the expectation value would be equal to, let's say we want to take the expectation value of some observable O in an ensemble, and so that would be defined to be the sum over all the states in the ensemble, where you have the probability and then the expectation value in the state I. And so this is just a weighted average of the expectation value for the observable over all the states in your ensemble, weighted by the probability that comes along with each state. Okay, and similarly, if we wanted to calculate the probability of some measurement giving a certain result, then that probability is going to be just the weighted average of the measurement result in these individual states. Okay. Now, the conventional states of a quantum system are examples, they're very specific examples of ensembles. And so in this more general context, we call these conventional states pure states. And a pure state would then be just equal to some state psi along with the probability 1. So that would be an ensemble that only has a single state in it. But if we want to talk more generally, then we're going to have ensembles with multiple states and multiple probabilities. And in this case, we use the terminology mixed state to describe collections of states with probabilities. Okay, so here's the key point for this video. So the important statement is that if we have any multi-part system and that system has a subsystem that I'll denote by A. Okay, and we want something that captures all of the information about that subsystem in the context of the larger system. Then the right answer is that there is one of these ensembles. So there is always an ensemble of states for that subsystem, okay, such that all expectation values and measurements on subsystem A in the full system match with the same thing, expectation values and measurements in the ensemble. Okay. And so this tells us that the correct way to describe a subsystem of a quantum system, where the quantum system is in a general state that could be entangled, the correct way to describe that subsystem is to say that the subsystem is actually in an ensemble. And so let's give an example where we have this state of two spins that we talked about in the previous video. So this is the rotationally invariant state, 1 over root 2 up, down, minus 1 over root 2 down, up. And so if we want to know what is the state of the first spin in this combined system, then the correct answer is that the first spin is in an ensemble, which is described by up with probability 1/2 and down with probability 1/2. Okay, and I want to emphasize that that is not the same as saying that it's in a superposition state. So for example, this state describes a spin which is pointing in the x direction. And so if I took the expectation value of the spin operator in the x direction, I would get h bar over 2. Okay. But for this ensemble, you can check that if you take the expectation value of the spin in the x direction or the z direction or any other direction, it will give you 0 for any n. Okay, and so that's what we wanted because this original state is rotationally invariant. So this is a generally true statement. I can take any quantum system, look at any subsystem, and if I want to describe the state that that subsystem is in and not carry around any extra information about all of the rest of the spins, then what I need to do is to specify some ensemble. Okay, and so in the next video, if you want, you can watch that one, and I will prove this statement and describe how would I go about finding this ensemble if I start with a general state.